Step 4 and step 5, as we'll see, are pretty much interchangeable. We are just going to start solving for the vector forces in our individual members, and we'll do so by drawing free body diagrams of our different joints. So I'm going to go ahead and start with joint A, although you could start with joint C if you wanted to. So, okay, we'll draw a free body diagram. So it's the same free body diagram that we're looking at over here, just of joint A by itself. And what do we have acting on joint A? Well, we got 0 pounds going to the right. We got 350 pounds going upward. We've got some unknown force going to the right at AD. So we'll call that vector AD going to the right. And we've got a downward and leftward force, some unknown force, of AB pushing down on joint A as well. And I went ahead and moved that up a little bit just so I had a little bit more room to work. But we can actually make this free body diagram even simpler. And we can do so by turning AB into its X and Y components. So what I'm going to do to show you, to demonstrate this, and something we've done before, is I'm going to redraw vector AB. And I'm going to add its X and Y components. I'm going to sketch out its X and Y components. And the reason why we're doing this is because if you think about it, you can replace vector AB with its X and Y components. So this would be ABY clearly, and if you choose this goes up for ABX, doesn't really matter. But if A squared plus B squared equals C squared, these can replace AB because that's all AB is. It's acting in the X direction to cancel out AD, and it's acting in the Y direction to cancel out 350 pounds. And so if you think about it a certain way, we can redraw our free body diagram in joint A, and everything else will be the same. Let's see what we got. Actually, let me just go ahead and copy this, or this part of this, and just, oops, that was a mistake. We'll just copy this and paste it right over here, and we'll just redraw it. But instead of drawing AB, we could just say, well, we got ABX going to the left. So let me get the right color here again. But we got ABX going to the left on joint A. And we've got ABY going straight down at joint A. And these replace AB. So, I mean, this says the same thing as this picture does, essentially. And so why is this so important? Well, now we got a clearer picture of what's going on. So I know ABY has to be canceled out by 350 pounds. I'm looking at it, there's only two forces going up and down. And so what does that mean? Well, we'll say the sum of all forces, and that looked terrible, but the sum of all forces in the Y direction at joint A. What does that equal? Well, it has to equal 0. There's only two of them. We've got ABY, let me put the right color here. We got ABY, which is going downward, plus our upward force of 350 pounds. And I can set my downward forces equal to my upward forces. Therefore, ABY has to equal 350 pounds. And so that by itself doesn't help us, or doesn't give us the answer that we need, but it does give us a start, as you'll see in just a second. So we can continue on. We can assume the same is true about the sum of all forces. In the X direction, that also has to equal 0. Well, how many of those do we have? We got 0 pounds, but we can go ahead and assume that that is nothing, so we don't even have to write that. We don't have to waste our time with that. We'll just say equals AD plus ABX. Get that color again. Plus ABX. And we can see what directions these forces are most likely going. ABX is clearly going to the left, and AD would clearly be going to the right. Therefore, I can set AD equal to ABX. And you might be thinking to yourself, well, now we're at a standstill because we don't know either of these variables. But we do know them if you look over here at this triangle that we've created. You might say, well, what triangle? I'm going to follow my tip-to-tip method we learned in our force vector part of our unit and redraw this ABX right here, creating a triangle for ourselves. And so we solved for this angle of this vector. That was the very first thing we did. This angle at angle A, this member is going the same direction. The vector inside the member is going the same direction of the member itself, and we solved that. It was 53.1 degrees. And so what do we know? When we know the opposite side, or imaginary side, to this triangle, and we know the angle. So we have everything we need to solve for AB, vector AB, which is right here. This hypotenuse is vector AB. And we have everything we need to solve for ABX. So I'm going to go ahead and start by solving for AB, because it doesn't really matter at this point where we start. We could solve for either one in any order. But so to solve for AB, okay, what do we have? Well, we know the opposite, and we're looking for the hypotenuse. So that's sine of our angle. What's our angle? We just said, well, that's 53.1 degrees. We don't need the degrees, actually. And we can set that equal to, well, the opposite, which is 350, divided by AB, and we don't know that. That's the whole point. Luckily, we can solve for that. And we're going to solve for that by we look at this as a math problem. You can use algebra to solve, multiply by AB, and then divide, and get AB by itself. But I'm going to look at this as sine of 53.1 as some number. And therefore, I can put this over 1. And if I put this over 1, I can cross multiply and divide. So I could say, therefore, we say 350. Let me keep everything consistent because I'm OCD. 350 times 1 divided by the sine of 53.1. We cross multiply and divide. We would say the sine of 53.1. Make sure we keep this all nice and OCD consistent. And we could set that equal to AB, and to solve for this, well, I just plug it in my handy-dandy calculator. Okay, we say 350 times 1, which is just 350, divided by the sine of 53.1. And what do we get? Well, we get 437.67, so we get AB equals 438 pounds of force. And a good rule of thumb is on the vector forces is rounded to the whole number. Just like over here, we rounded to the 1 decimal place for our angles. And you might say, well, that's great, but what about ABX? Well, ABX, we could do the exact same thing. We could use cosine. We could use, so that'd be adjacent over hypotenuse. We just solved for our hypotenuse here. Or we could use Pythagorean theorem. We could do a squared minus b squared, c squared minus b squared equals a squared. But neither of those would be as precise as using tangent. And the reason why tangent would be the most precise, so let's go ahead and say ABX. To solve for this, we will say tangent. The reason why tangent would be the most precise is because it's using our most precise value. We rounded this 438. We didn't round this 350. It was exactly 350 according to our math. So we see the tangent of our angle, which is 53.1 degrees still. That hasn't changed. We set that equal to, our tangent is opposite, so that's opposite is 350, divided by adjacent, which is ABX, which is what we're looking for. And I decided since we've already kept everything color-coded, we might as well keep that going. But this is essentially the exact same thing. We would just put this over 1 and cross multiply and divide. 1 times 350 divided by the tangent of 53.1. We could say, therefore, ABX equals, and well, I don't know, but I'm just going to type it in my calculator. It's 350 divided by the tangent. Divided by the tangent of 0.1 degrees. So what do we get? We get a vector force at ABX of 263. I believe that was 263, right? Yeah, it rounds up to 263 pounds. And that by itself isn't much, but you remember that plugs in right up here. Okay? And I drew that a little bit quickly, but I had to improvise. But if that is true at ABX, then it has to be true at AD. So this is 263 pounds as well. Therefore, we've already solved for 2 of our 3 vector forces.